Hello everyone, welcome to my channel. I'm Yue Aiwuli. Today I'd like to invite my supervisor, Professor Robert Mann, from University of Waterloo to share something about the black hole superposition. So,
Hello, everyone.
hello
Glad to be
everyone.
here.
Could you please briefly introduce what is a black hole superposition or what is the superposition of spacetime?
Well, quantum superposition is a phenomenon that is very much like what we experience in everyday life. It basically refers to a situation in which a given system can be in two different states at once, a ground state and an excited state, or perhaps here or there, or something of that nature. Now, we don't see this in everyday life. Whenever we measure the location of something, we find it's either here or it's here. Uh, what happens in quantum physics is that when a measurement is made, then a particle or a quantum system is localized into a particular state. But before that occurs, it does not have to be localized or collapsed into a
Mhm.
particular state. So that's the notion of superposition. So black hole superposition is simply the idea that a black hole can be in two different quantum states
Mhm.
at the same time. In other words, in a combination of states, maybe of having a light mass and a heavier mass. It's a phenomenon that we expect will occur in quantum gravity. And the reason for that is that quantum physics, for all other phenomena, allows superpositions, a phenomenon we verified many times in the lab. So we therefore expect gravity will
Mhm.
also allow superposition. But since gravity corresponds to what we mean by the curvature of space and time, a superposition in quantum gravity would presumably be a superposition of two different space times. And if the space time is associated with a black hole, then a superposition of two different black hole space times really would be a superposition of two different black holes.
Yeah, thank you. And there is an experiment called Schrödinger's cart in quantum mechanics. And do we have a black hole Schrödinger's cart, something like that?
Well, if the black hole were large enough, then presumably the answer is yes. This has not been very well studied, but you could imagine an experiment where the black hole is coupled to something else, some other quantum field,
Mm-hmm.
or some particle that's orbiting the black hole. And you could imagine that if the particle, let's say the particle is orbiting the black hole, if it's a spin up particle orbiting, the black hole might be in one state, but if it's spin down, it might be in the other state. And then depending on how we measured that particle, if it were up or if it were down, then we would have the black hole go into one of two different macroscopic states, very similar to the Schrödinger cat.
I see. Why do you think it is significant to study the space-time in superposition?
I think it's significant to study space time and superposition because it's an effect of quantum gravity. And what we've been able to do in my research group, building off work of other people that work on quantum reference frame groups, such as Czesław Brutner's group in
Mm-hmm.
Vienna, for example, is we have been able to describe black hole superpositions without having a full quantum theory of gravity. This is somewhat analogous to the way Niels Bohr was able to describe a quantum hydrogen atom without having a full theory of quantum mechanics, which took another dozen years before uh, quantum mechanics emerged. So I think it's incumbent upon us to study effects of quantum gravity that
Mm-hmm.
we expect to be there. And if the full theory comes about and says the effects are a little bit different, well, so be it. But I think we will learn something from the endeavor of making use of our knowledge of black holes, quantum reference frames, and
Mm-hmm.
so on to study the phenomenon.
See, so it's like lab to testing quantum gravity, right?
Yes, it's a theoretical laboratory for testing our ideas about quantum gravity. Absolutely.
I
Yes.
see. So, for a specific question, some of my followers ask what is the undirect detector. So, could you please explain it?
An Unruh DeWitt detector is a theoretical device that consists of a system in two possible quantum states, a ground state and an excited state. So,
Mhm,
in some sense, it's a qubit that can be in one of two states, up or down,
mhm,
ground or excited. It was originally developed as a theoretical device to show that a uniformly accelerated uh, observer would actually experience physical effects. If that
mhm,
observer had an ensemble of such two-level detectors, those detectors would then, if they were uniformly accelerated, have a thermal distribution. And so that got people really believing that the Unruh effect, namely the effect that a uniformly accelerated observer experiences a thermal bath of radiation, it got them to see that a hypothetical physical device actually would become thermally excited or thermally populated. We don't yet have actual Unruh DeWitt detectors, but there are serious laboratory efforts to
mhm,
construct them. The applications of these things so far in physics have to do with understanding the entanglement of the quantum vacuum,
mhm,
quantum communication protocols between different detectors, quantum teleportation processes, and so
mhm.
on. So they are hypothetical devices that we hope can be realized one day in the lab or approximately realized one day in the lab.
Yeah. Thank you so much for sharing this beautiful physics
Well, thank you.
in black hole superposition and also the undivided detector. So
Happy to
that's
do
it.
it.
Thank
Thank
you.
you. Bye bye.